So here in this video we are going to discuss the questions that appeared in thermal and statistical physics in NET examination June 2020. So the first question that I am going to discuss, it's related to black body power radiation. Okay, power radiated by black bodies. The statement is the temperature of two perfect black bodies A and B are 400 Kelvin and 200 Kelvin. So let's cite the information that is given to us. So we are having two black bodies and they are labeled as A and B. Temperature of black body A is 400 Kelvin. Okay, and let's cite the information for the body B on the right hand side. To TB, this is equal to 200 Kelvin. Okay, the area of black body A, area is equal to twice the area of B. If area of black body B is area, it's given the statement of the question, area of black body B is A. Okay, so now we have to find the ratio of the power radiated by body A to body B. What is PA by PV? Okay, so we will recall that the expression for the power radiated by a black body is given by power radiated by a black body. This is equal to A, area, and then emissivity sigma T power 4. Here A is the area of the black body and it is the emissivity of the black body. So emissivity for black body, it is taken as 1. Sigma, it represents the Stephan constant. Stephan's constant, and T represents the temperature of the body. So based upon this information, if we calculate the PA by PV, so this comes out to be area of the black body A, which is 2A. Okay, and then sigma. So in fact sigma and sigma, that will cancel with each other. So 2A sigma T, TA power 4. TA is how much? It's 400 Kelvin. So 400, its power 4 divided by area of black body B, which is A, and then sigma, and then TV power 4. TV is 200 Kelvin, 200 Kelvin, and its power 4. So after cancelling the common term, sigma will cancel with sigma, A will cancel with A. So ultimately we are left with a factor of 2 multiplied by 2 power 4, and this turns out to be equal to 32. Okay, so 32, the option C is the correct one here. We are given two ideal gases in a box which are initially separated by a partition. Okay, so let's try to understand the statement of the problem here. So we are given two boxes containing ideal gases and they are separated by this partition here that I have drawn as a line here. So it's also given that N1 B1 and N2 B2 be the numbers of particles and volume occupied by two systems. Okay, when the partition is removed, so when we remove this partition, okay, the pressure of the mixture at an equilibrium temperature. So when the partition is removed here, so gas molecule from this side, they will move in this direction, and gas molecule from this side, they will start moving in this direction. So ultimately we will have a mixture of these two gases, and at the end, when we just remove this partition, there is a non-equilibrium situation, and after a sufficient time is given for the system to settle, equilibrium is attained. After removing the partition, and equilibrium is set up, so that final temperature of the composite system. Final temperature of composite system is T. So it's given to us. Okay, so now we have to find the expression for the what is the common pressure when equilibrium has been established. Okay, so when we are making a common system or composite system, the total volume is B is equal to B1 plus B2, that's the total volume, and N is equal to the number of mole, the total number of moles in the composite system, that will be N1 number of mole corresponding to system 1 plus N2 number of mole corresponding to system 2. So here, because we are not given the number of moles, we are simply given the total number of particles, but we can evaluate the number of moles from this information. So the number of moles for the given number of molecules will be in the system 1, this is equal to the number of gas molecule in system 1 divided by the Avogadro number, which I am denoting here with Na, where Na denotes the Avogadro number. Okay, so let me write here, it is Avogadro number. Avogadro number. Okay, and then plus the number of moles of the system 2, which is number of molecule present in that system, and divided by again Avogadro number. Okay, and this can be rewritten as N1 plus N2 divided by Avogadro number. So this number will give us the total number of moles in the composite system. Now once the equilibrium has been set up, so that means, because we are having a mixture of two ideal gases, so when they are allowed to mix, and again the system when it come back to the equilibrium state, so this composite system is supposed to satisfy the ideal gas equation. Okay, PV is equal to nRT, where T represents the final equilibrium temperature, and N is the total number of moles in the composite system, and V is the final volume, and P is the final pressure. So we have to determine what is P here. Okay, so from this relationship, P is equal to the number of moles multiplied by R multiplied by common temperature T and divided by the common volume B. So here we will substitute the value of all these variables for the composite system. So N is equal to N1 plus N2, N1 plus N2 divided by Na. So this is equal to N. Okay, and then R we can rewrite R to be equal to N Avogadro number multiplied by Kb. So these two numbers, when you multiply, they gives you R, the gas constant. Okay, so I am rewriting this in terms of Boltzmann constant, because here the options that are given here, they are in terms of Boltzmann constant. Okay, not in terms of R here. Okay, so NR, then the common temperature of the system, and then divided by the common volume, which is B1 plus B2. So some of the terms here will cancel, so Na will cancel with Na. So finally we are left with KBT multiplied by N1 plus N2 divided by B1 plus B2. So this is our final answer, and this matches with option B. So therefore option B is correct. Let's continue with the next question. The statement is, an idealized atom has a non-degenerate ground state at 0 energy and a G-fold degenerate excited state of energy E. So let's draw the energy level for the given system. So we are having two energy level system whose ground state energy E, it's given to be 0, and excited state energy, it is E. And it's also given that degeneracy of the ground state, let's call that as G1, that is degeneracy, this is equal to 0, it's non-degenerate, so not 0, it is 1 basically, sorry. Okay, and degeneracy of the first excited state G2, this is equal to G fold. Okay, and then in a non-interacting system of n such atoms, so number of non-interacting atoms in the system is equal to n. So it is a n particle system, you can say. such atom, the population of the excited state may exceed that of the ground state above temperature T. So it's also given when the temperature of the system exceeds this value E, when it is greater than T, it's greater than E upon 2 kb ln2. So in that case, if we assume that number of atoms in the excited state they are n2, here if we assume that number of atoms in the excited state they are n2 and number of atoms in the ground state they are n1. So when this condition is of temperature is satisfied, so then n2 exceeds n1. Okay. So the minimum value of G for which this is possible is, so this, when temperature exceeds this value, n2 is greater than n1. So that means when temperature is equal to E upon 2 kb ln2, so in that case we can say that number of atoms in the excited state that become equal to number of atoms in the ground state. So we will make use of this this point here to evaluate the minimum value of G. Okay, so that is required to fulfill this condition. Okay, so now before we proceed further, we will determine the partition function for this given system, and then we will find the probability of occupying energy state E is equal to 0 and probability of occupying the energy state E. Okay, so the partition function for this system can be written as Z, that is sum over all energy state Gi exponential minus beta Ei. Okay, and this is further equal to, because we are having only two energy states, so this is equal to G1 exponential minus beta E1, which is equal to 0 basically, plus G2 exponential minus beta E2, which is the first excited state. Okay, and this is further equal to G1 is how much? It is 1 here. 1 exponential 0, E1 is 0. Okay, this is 0, so when you will put it here, e power 0, that will give you 1 basically. Okay, plus G2 is G here, G exponential minus beta multiplied by energy of that energy level. Okay, so this is basically equal to 1 plus exponential minus beta E. So that is the partition function. Let's call this as equation 1. Now we can determine the probability that the ground state is occupied. Okay, it's 0 and this is E, and degeneracy is G, and here it's 1. So now let P1 denotes the probability that the ground state is occupied. So then P1 is equal to exponential minus beta multiplied by the energy of the ground state, which is 0, divided by the partition function. Okay, so this is equal to 1 by Z. Let's call this as equation 2. And similarly, the probability that excited state is occupied, this is equal to exponential minus beta E upon, with the degeneracy factor G exponential minus beta E divided by Z. Okay, so this is equation number 3. Okay, now we can write the expression for the number of particles as we considered in the beginning. Let's say the number of particles are n1 here and number of particles are n2 here. So we can write expression for n1 and n2 in terms of p1 and p2. Okay, so let's see because the probability of occupying the energy the ground energy state, it's p1. So the number of particles, if there are n1 in the ground state, so n1 it's connected to the p1. It's the fraction of n basically. Okay, n multiplied by probability of finding the probability of occupying the energy state, the ground energy state. Okay, similarly we can write expression for n2. It's n multiplied by the probability of occupying this energy state. So these two expressions, they satisfy the condition that n1 plus n2, this is equal to n multiplied by p1 plus p2, and p1 plus p2, that will be unity, so that means this is equal to n. So that means the total number of particles, that is simply equal to n1 plus n2, that is equal to n, as it should be. Okay, now we have to determine the minimum value of the degeneracy factor G for the excited state, so that n2 exceed n1 when temperature exceeds the given value. Okay, so that means, so here we will apply the condition that when n2 is equal to n1, so that means np2. N2 is how much? It's np2. So this implies n times p2 is equal to n times p1. So n will cancel. So that means p2 is equal to p1. So, okay. So that means p2 is how much? G exponential minus beta e upon z. This is equal to 1 upon z. So this will cancel. So that means g exponential minus beta e, this is equal to unity. Okay. So n2 will be equal to n1 for what temperature? As we said in the beginning, T is equal to E upon how much? What is given? It is E upon 2 kb ln2. E upon 2 kb ln2. Remember here, for T exceeding this value, the number of atoms in the excited state N2 will exceed N1. Okay. So T is equal to this quantity that will give you when the number of atoms in the excited state and ground state, they are equivalent to each other. So here in this equation, let me call this as equation 4. So in equation 4, we will substitute the value of T, this value of T here. Okay. So that means G, from equation 4 I can write G is equal to 1 upon exponential minus beta e. So ultimately it becomes G is equal to exponential beta e. Okay. So this is equal to further e power beta, that is e upon kb into 1 by t. Okay. So we are going to substitute the value of t here. So this becomes equal to exponential e divided by kb, and what is 1 by t? Okay. T is equal to, so here this will become 2 kb ln2 divided by e. So e and e will cancel, kb will cancel with kb. So we are having e power this one, and this is equal to e power ln 2 power 2, and this is equal to 4. So therefore G is equal to 4. Okay. So when this temperature is equal to this expression, so the minimum value of G that is required to fulfill that condition, that G is equal to 4. And when T exceeds E upon 2 kV ln2, okay, when this is larger than this, then this will result in N2 greater than N1. Okay. So only for T equal to this expression we will get N1 is equal to N2. So therefore our right answer is B, G is equal to 4. Let's continue with the next question. The statement of the question is the Hamiltonian of a system of n non-interacting particles. So we are given a system of n non-interacting particles. Whose Hamiltonian is given through this expression. Okay. In one dimension. Okay. So here the first term is that's a kinetic energy term, the ordinary kinetic energy term, p square by 2m, and the second term is it's having fourth power in displacement, so plus lambda by 4 xi4, and it's given that lambda is greater than 0, it's a constant, and pi and xi are the momentum and position respectively of the ith particle. Now we have to find the average internal energy of the system. So we can the average value for the first term can be immediately evaluated by making use of the equipartition theorem. Okay. So what does the equipartition theorem say? That each squared energy term. Okay. So based upon the result from equipartition theorem, whenever we are having squared energy term, so each squared energy terms contribute half kVt to the average energy. Okay. So here therefore we conclude from equipartition theorem that the average value associated with the first energy term, that is pi square by 2m, so this will be 1 by 2 kVt. Okay. So this is simple. Okay. Now let's try to see how we can solve the second part. So now we have to determine the average value of the second term, that which is lambda by 4 xi4. Okay, if I call the second term as if I note this as ei, okay, this is equal to lambda by 4 x4. So here lambda by 4, it's nothing but it's simply a constant. So what I can do is I am going to replace lambda by 4 with a constant alpha and then x power 4. Okay, so basically we have to determine the value of ei, the mean value of ei, which will be equal to the mean value of alpha x4 basically. Okay, now so here I'm going to discuss here the very general results when we are having such type of expression for energy. Okay, so let's take the very general case here. If we assume that energy has dependence on the displacement as E is equal to alpha x power n. Okay, so let's call this as equation 4. So now we want to determine the average value for this quantity. What is average here? Okay, so now from here, from equation 4, I can rewrite. So this implies dE, that is equal to n alpha x power n minus 1 dx, or this is further equal to, after rearranging the terms, ne upon x dx. Okay, and from here we can write dx in terms of dE. Okay, so this becomes dx, this is going to be equal to x upon ne multiplied by dE. Now we can substitute for x from here, so x will be e power 1 by n divided by alpha power 1 by n. Okay, so we are going to do that. Okay, so in terms of that, the expression reduces to e power 1 by n divided by, so this n as it is, okay, and then constant alpha power 1 by n, then e as it is, e and multiply by dE. Okay, so and this is further, after rearranging all these terms, this comes out to be equal to some constant k. So I'm absorbing all these terms, n alpha power 1 by n in constant k here, and e power 1 by n minus 1 dE, where k is what? K I have taken as k, well, it's simply a constant. K is equal to 1 divided by n alpha power 1 by n. Okay, now we have to determine the average value of E. So let's see how we are going to do it. E, this is equal to the simple relationship for determining the average of a physical quantity from 0 to infinity, because we want to determine the average value of E exponential minus beta E, and then the variable here is x. Okay, then divided by 0 to infinity exponential minus beta E dx. Okay, so this will be equal to further 0 to infinity e power 1 by n exponential minus beta E dE. So we have replaced now dx. Okay, dE upon 0 to infinity e power 1 by n minus 1 exponential minus beta E dE, and this can be rewritten as kVt in terms of gamma function, kVt 1 plus 1 by n divided by gamma 1 by n, and this comes out to be kVt upon n. So this is very simple results at the end. So now in our case, what is the value of n? So here in our case n is equal to 4, the exponent is 4. So therefore this implies that the mean value of the term that we are looking for in our results, so the mean value of ei, which is equal to lambda by 4 x4, that is nothing but kBt by 4. So therefore the total value, the total energy per, the average energy per particle in the question that is asked, that is average energy per particle will be how much? The contribution from the first term, which is kVt by 2, plus contribution from the second term, which is kVt by 4, and after solving it, this will come out to equal to 3 by 4 kVt. So let's see with which option it matches. So it matches with B, so therefore option B is correct here. Let's continue with the next question. The statement is the energy density I of a black body radiation at temperature T is given by Planck's distribution function, which is given here I is a function of the frequency and temperature, which is equal to 8 pi nu square upon c cube into h nu upon e power h nu upon kt minus 1. Okay, let's call this as expression 1. Okay, now for the given condition, the ordinate is, okay, so we are given that the function I nu t for two different temperature, it's T1 and T2, it's shown here. So when we plot this function equation 1, so for this temperature T1 and T2, we are having these two different graphs. We are obtaining these two different graphs here. Now if the two curves coincide with I nu, if the two curves coincide when we are plotting I nu t, multiplied by nu power a, it's plotted against nu power b divided by t, then the value of a and v are respectively. So that means we have to somehow eliminate, we have to use this function as a x and this as a y here. Okay, so let's see for what value of a and v this is going to happen. So let's try to evaluate the ordinate first, which is for the given condition by, which is equal to the I nu t, the given energy density function, and then multiply it by nu power a. So this will become equal to 8 pi, and then here we are having nu square and nu, that will give us nu power 3, and then when we will multiply it by nu power a, okay, so that will be nu power 3 plus a, okay, and then divided by c cube, this, okay, into h divided by exponential, here the same factor h nu upon kt, and here we are going to multiply by nu power b and nu power minus b, so ultimately it will not make any difference, okay, and then minus 1 here. Okay, let's call this as equation 2. Now we are given that this function y, it has to be plotted, this function y has to be plotted as a function of nu v power t. So that means we will take x is equal to nu power b upon t. Okay, we'll call this as equation 3. Okay, so then when using x is equal to nu v by t, and if we will make use of this expression here in equation 3 here, so that means we are going to eliminate basically t from these two equations. Okay, so then under those conditions the expression 2 reduces in terms of x is equal to nu v by t, expression 2 becomes equal to y. So 2 implies then y, this is equal to I nu power a and equal to 8 pi h, the constant terms we are taking outside, c cube, and then nu power a plus 3, and then divided by e power h nu and power minus b plus 1, okay, divided by kb, and then we have replaced we have replaced nu b by t with x, so that's why we are having x here, okay, and then a factor of -1 in the expression. We call this as equation 4. Okay, so now we see from expression 4 that when a is equal to -3 and b is equal to 1, so this expression becomes the equation 4 reduces to y equal to 8 pi h upon c cube upon exponential e power hx upon kb minus 1. So let's call this as equation 5. So when y is plotted, when y as a function of x is plotted, so then the temperature dependence disappears. Temperature dependence disappears, and both curves will coincide. So therefore the correct option is B. A is equal to -3 and B is equal to 1. So D is the correct one here. So let's continue with the next question. So the statement of the question is: the Hamiltonian of a system of 3 spins is given by H is equal to J into S1 S2 plus S2 S3, where Si equal to +1 or -1 for I is equal to 1, 2 and 3. Its canonical partition function at temperature T is given by. So before we work out the partition function, it is essential to look for the possible microstates that this 3-spin system can acquire. Okay, so let's try to understand this problem. So the Hamiltonian is given as H equal to J, where J is basically the exchange integral, into S1 S2 plus S2 S3, and each spin Si can take value of +1 or -1. So here we will make an assumption that when the spin it is pointing in the upper direction, so we will take it as +1, and when it's pointing in the downward direction, so we will take it as -1. Okay, and I can take a value from 1 to 3 because we are having a 3-spin system. Now the number of microstates, one can quickly check it. So when we are having a 3-spin system, so the first spin has two options, equal to 2. What are those options? Either up or down. Okay, so we are calling this as +1 and this as -1. Okay, similarly second spin has options. How many? It's also having 2 options. Similarly third spin has how many options? 2 options, up and down. Okay, because this up and down option which are taken by any individual spin, they are independent from each other. Okay, irrespective of the spin of the other spin, it's independent. Okay, so therefore total microstates will be, for this system, total microstates will be 2 power 3. Okay, or in principle when we are having a system of n spins, so total option will be 2n here. So here we are having 3-spin system, so 2 power 3, and that is equal to 8 microstates. Okay, So let's try to work out all these microstates, and after that, knowing the distribution of the various spins, this spin system, we will be able to determine the corresponding energy of the microstates. So for that we need a little bit extra space, so I'm going switching to the next page. Okay, so let's work out the different microstates, the 8 microstates that I just mentioned. So we are going to draw a table. S1 stands for spin 1, S2 for spin 2, and S3 for spin 3. So here E is the total energy of that particular microstate. Okay, so I will start with the situation where all the spins, they are pointing in the upper direction. So I will take 1, 1, 1. So in this case the exchange energy will be where I'm going to write here the integral here, J multiply by S1 S2 plus S2 S3. So I will calculate here it only for 1, and then similarly we can work it out for the rest of the arrangements, spin arrangements. So here for this particular arrangement of this 3 spins system, so J S1 is 1 multiply by 1 S2 plus S2 is 1 here, 1 multiply by, it's S3 not S2, multiply by 1. So 1 plus 1 will give you 2. So here the energy is 2J. Okay, so here I am writing 2J. Okay, now similarly now we will start with spin flip. Okay, 1 1 minus 1. So this will gives us an exchange energy of 0. How? First multiply 1 into 1, that will give us 1, and 1 into minus 1, 1 into 1 1, and this 1 multiplied by minus 1, that will give us minus 1. So ultimately we will have J into 1 minus 1. So that's why a 0 here. Then 1, the central spin is in the lower direction, 1. So 1 into minus 1 minus 1, and minus 1 into 1, that will give you another minus 1. So this will gives us a exchange energy of minus 2J for this microstates. Okay, now let's say this spin is in the downward direction, pointing in the downward direction, up, up. So minus 1 into 1 minus 1, and then 1 into 1 1. So again this will give us 0. Okay, so now instead of 1, now we will have 2 spin flip at a time. Okay, let's say first 2 spins, they point in the downward direction, so that's why I'm taking it as minus 1 and then plus 1. So this will gives us minus 1 into minus 1 plus 1, and then minus 1 into 1 minus 1. So this will lead to a 0 energy. And now 1 and then minus 1 and minus 1. So this will gives us 1 into minus 1 minus 1, and then this will gives us a plus 1. So again 0. Okay, and then the third option for the 2 spin down and 1 spin up. So extreme 2 spin pointing in the downward direction, they will give us minus 1 and then minus 1. So this will give us minus 1, and these 2 will give us another minus 1. So ultimately minus 2J. Okay, now the last option where all the spins, they are pointing in the downward direction. So minus 1 minus 1 minus 1. So this will gives us a plus 1 and plus 1 from here. So this will give us an energy of 2J. Okay, so this way we notice that we are having the microstates with 0 energy. Okay, when E is equal to 0, how much is the degeneracy? 1 2 3 4. So G is equal to 4 here. And when E is equal to 2J, what is the degeneracy factor? 1, and then okay, here it will be plus 2J, sorry. Okay, so it is the second one here. So G is equal to 2, and when E is equal to minus 2J, and let's see how much is G? 1 and 2, again 2. So now it's known to us that the corresponding energy for the microstates and what is the degeneracy for the respective microstate. So from here we can write the expression for the partition function, which is Z is equal to summation over I gi exponential minus beta EI. Okay, so let's move to the next page, and then we will write the expression for the partition function. Okay, so Z, the partition function, this is equal to summation gi exponential minus beta EI. Okay, so based upon the information that we wrote in the previous page here, on this value, from here we can write the expression for the partition function. So for E is equal to 0, we are having 4 microstates. Okay, so the corresponding contribution in the partition function will be 4 exponential minus beta multiplied by 0, so that will give you E0 here. So ultimately a 1 will come here, plus then we have degeneracy of 2 with energy beta j. So the partition function contribution will be exponential minus 2 beta j when energy is beta j. Okay, and then another factor with a degeneracy of 2 and energy of minus beta j, so that will give us 2 beta j. Okay, so after that we are going to rearrange all these terms here. So what I will do is so here this will give us only a 4. Okay, so I'm going to take it at the end of this expression. Okay, so this will give us, so I'm going to take a factor of 2 common from these two terms, so 2, and then inside we have exponential minus 2 beta j plus exponential 2 beta j, and then a factor of 4 into e power 0, which is 1. Okay, and after that I can rewrite this as 2 outside, and inside the bracket again exponential minus beta j plus exponential beta j, its square, and then here when we will expand this this function, then we will have a factor of 2 here, so I am subtracting it again from here, and then factor of 4. Okay, and this is further equal to 2 multiplied by 2, and then e power minus beta j plus e power beta j divided by 2 and its square. So here 2 into 2 minus 2, that will give us minus 4, and that will cancel with 4, so we are only left with the term inside this bracket and this factor 2. Okay, and this is nothing but this is equal to 2 multiplied by 2 cos hyperbolic beta j and its whole square. Okay, its whole square. Okay, this can be rewritten as 2 multiplied by 2 cos hyperbolic jy and its so it's a whole square. Okay, and then only whole square of this quantity. No, this like this. Okay, sorry. Okay, so this is a final answer. So let's see with which option it matches. Okay, so this matches with B. So B is our correct option. Let's take a look at the next problem. The statement is, for an ideal gas consisting of n distinguishable particles in a volume V, the probability of finding exactly 2 particles in a volume delta V much smaller than V in the limit n b approaching infinity is. Okay, so we are given a situation where it's basically the thermodynamic limit. So we are given a system where n and v both approaches infinity. So that means we are talking about a very large number of particles, and a system having very large volume, and this approximation is called as thermodynamic limit also. Thermodynamic limit. Okay, so we have to find the probability of finding exactly two particles in this case. Okay, so here suppose V represents the entire volume, and suppose here we are having a very small volume delta V here. It's very small compared to the total volume. Okay, so we have to find the probability that this volume delta V will contain two particles. So here we can make use of Poisson distribution. We can make use of Poisson distribution, where probability is given by probability is given by Pn, that is equal to mu power n divided by n factorial e power minus mu. Okay, so when n is quite large, when n, that's the number of particles, it's quite large, is very large, one can write mu, which is called the moment also, mu equal to n, then multiply by the probability, which is delta V by B. Okay, delta V by V. Okay, now for n is equal to 2, this expression reduces to n is equal to 2, small n, the n for two particle, P2 will be mu power 2 upon 2 factorial and e power minus mu, which is this n delta V by e power minus mu. And after substituting a value of mu from this expression into this equation, okay, so we are left with P2, it comes out to be equal to n delta V its square divided by 2v square e power minus n delta V upon B. So this is our final answer, and it matches with option C here. So therefore C is correct option.